Welcome on stage, Jon.
Thank you. Good afternoon, everyone. Thank you, Kasia, for that introduction and for the opportunity to talk to you today about poLight technology and our applications.
It's a pleasure to have you.
Yep. And thank you. It's my first time at one of these events, and I've been impressed with what I've seen so far.
Nice.
Okay, so my background is in electronic engineering. I've spent more than 20 years working in image-related fields such as image sensors, camera actuators, and tunable lenses. I've been with poLight for 3 years, where I'm VP of Business Development. And today I'm going to give you an introduction to poLight as a company. I'm going to talk to you about the poLight technology platform, applications for that platform and for our products within AR, VR, and MR devices. And I'll talk in detail about our core products of TLens and something called TWedge, which I'll explain is a new product for us. So, poLight's a Norwegian company, founded in 2005. Our main products are Tunable Optics. We have a manufacturing business model. We are fabless for everything, with the exception of the polymer that's the core of our tunable products. We are based in a town called Horten, which is about an hour outside of Oslo, the capital of Norway. And although we're a Norwegian company, less than a third of our people are based in Norway. The rest are distributed around the world. So I'm based in the UK, where we have an engineering centre. We also have engineering in Taiwan and in Tampere in Finland. And we've got customer support offices in the Bay Area of the US West Coast, in Shenzhen, and other sites around the world. As of today, we're 38 people. We've got a strong portfolio of IP relating both to the tunable lenses themselves and their applications and end devices. And we're listed on the Oslo Stock Exchange. To give an indication of some of the areas where our lenses are used, here are some of the customers that we can talk about. Our lenses are used in smartphones. So there you see a phone from a company called Meizu, called the 20 Infinity. We provide the T-lens that goes into the selfie camera to do the autofocus in the front camera on that device. We're in AR headsets, such as the Magic Leap 2 and several other AR headsets, and other consumer devices, such as smartwatches, webcams, etc. In industrial markets, we're in a lot of machine vision applications, such as barcode reading, industrial cameras, and robotics, and the like. To explain what we do at poLight, the easiest way is to explain what we call the poLight technology platform. Essentially, this is a combination of piezo actuation and the control of the piezo, deformable optical membranes, and the optical polymer, which is the core for everything that we do. Our first product that we shipped is called T-Lens, and that's the device that you see at the bottom there. T-Lens is an electro-tunable focusable lens. So what I mean by that is that you can change the power, the focusing distance of that lens element by controlling the electrical signals to it. It's a voltage controlled device, so you simply apply a voltage to it. In the cross section there, you see the elements of the technology platform that I mentioned. The top is the deformable membrane. That is formed at a wafer level, and the piezo actuation and the membrane are formed together as part of that wafer process. Beneath that sits the optical polymer, and as the T-lens operates, as we change the voltage on the piezo, that piezo bends and deforms that top membrane into a spherical shape. The polymer that sits behind it merely passively follows the shape that's described on that membrane, and the combination of the two generate a focusing lens to focus light. That's basically the basic operation of what we call the T-lens. We make these T-lenses in different sizes. Our core offering is the two parts that you see on the left there, silver and silver premium, both of which are in mass production and shipping to customers now. The difference between these parts is the aperture, the size of the usable lens, and the optical power range that can be achieved on the T-lens itself. So silver has an aperture of 1.55 millimeters and a maximum optical power of 14 diopters. Silver Premium has a larger aperture but a smaller optical power. And in addition, on our roadmap, we have samples now of a product called Platinum with larger again aperture that we expect to be in production maybe in about 18 months, depending on customer demand. All of these parts have anti-reflective coatings on the top and the bottom surfaces, which means we get very good transmittance. We've got two generations of AR coating. The main coating that we have on the mass production products today, and a new coating that we're developing for future products. Between those, they can achieve transmittances of between 94 and 98% in the visible spectrum. So why do we do this? What are the benefits of using a T-lens? It's got to be said, the main one is power consumption. And when we talk about low power consumption, we really do mean low power consumption. So typically a T-lens would be consuming about 1 milliwatt in constant use. And that compares with competing technologies such as VCM or SMA, which might be hundreds of milliwatts. In addition, we're very fast speed. And for us, fast speed means about a millisecond settling times on transitions. Which again is much faster than many of the competing technologies, either mechanical or thermal. I mentioned the actuation is actually built right into the top membrane on that piezo surface, so there's no need for external actuators. This means that there's no mechanical overhead around about the T-lens. It means that you can dust seal it very well into the camera modules, and it means that you can place the T-lens inside the lens barrel, as treating it just like any other lens element. We call that an add-in design, and it's very important to many of the things that we do. It's extremely small size, partially due to the fact there's no external actuator, partially due to the fact that it's an extremely effective optical system. And then finally, we can make athermal optics. So that bears a little bit more explaining. As I'm sure you're aware, most optical systems will have a thermal dependency, whereby the performance, easiest considered to be the focal point of the system, will change depending on the temperature of the system. T-lens also has a thermal dependency, but by good design and good control of the materials, we're able to design our parts such that the thermal dependency of our part is about equal magnitude, but opposite sign or direction to any variations in rigid optics. So when you combine the two, they cancel each other out, and you arrive at an optical system that's almost entirely athermal. To make it easier for our customers, we sell the T-lens and our products together with the driver chips. The part that you see on the screen now is what we call PD50LE. That's a driver ASIC that we make that works alongside the T-lens. It really is as small and as simple as we possibly can make it. It's pin limited at 2x3 pins, 2 pins for power in, 2 pins for I2C control, and 2 pins to connect to the T-lens. It's 1.3 by 0.9 millimeter, which is extremely small and very easy to integrate into the camera modules or our customer products. I mentioned earlier that we have a fabless manufacturing business model. The only product that we make ourselves is the optical polymer. That's essentially the secret sauce. We like to keep that very close to ourselves. We manufacture that in Horton at headquarters. A typical T-lens product contains about 1 microliter of that polymer. So 1 liter of the polymer, very easy to transport, can make, in theory, about 1 million lenses, assuming, of course, there's no losses or you don't spill any. So it's extremely scalable, making that in Horton. It's extremely easy to transport. It's got a long shelf life. We hold buffer stock at our assembly partners, and that's simple to do because of the the small amount of it that's needed. The top membrane, the part that comprises both the deformable membrane and the piezo actuation, that's made for us by ST in Agrate, and that's made in a wafer MEMS process. We get those 8-inch wafers from ST, we dice them into individual die, and then they are assembled at our assembly house using relatively straightforward pick-and-place machinery. That's done at a company called Tongseng in the Philippines, which is a major packaging and manufacturing supplier for all of the semiconductor industry. So again, with very high volume capability. And we do 100% final test on every single T-lens, and every single T-lens has unique data that stays with that T-lens and is traceable through the entire production flow. And assuming our customers keep track of what they assemble, it's also traceable through the end customer products as well, back to the individual batches of T-lens and individual final test data for each T-lens is manufactured. The driver IC is just a chip. It's manufactured in a standard chip fabless foundry process. So in AR, what are the applications for these tunable lenses? Well, there's the obvious ones. There's many cameras in AR devices. There's cameras used for things like passing video through in pass-through applications. Cameras used for capturing images to show the world view of the user. And cameras used for mapping and SLAM and things like that. All of these cameras may benefit from active focusing, autofocus, and many of them will benefit from athermalization, where it's important that the camera focus is fixed or known across the wide temperature range that can happen in AR devices. There's AR glasses and spectacles are actually quite a challenging thermal environment because there's a lot of processing happens in the device, and there's a very small area with which to dissipate any heat that you generate in the device. And of course, the maximum allowable temperature on the external surfaces are limited because it's right next to your skin. So it's a difficult thermal environment, and cameras and many of the other devices can see large temperature changes and also thermal gradients across them. So athermalization in these applications can be extremely important. Outside of cameras in AR applications, we also play in the display space. So again, athermalizing some of the projection optics for conventional micro projectors used in these devices. T-lens can be used there to take out thermal variations. For LBS or laser beam scanning, retinal scanning type systems, T-lens is used to control the focusing, or more accurately, the collimation of the laser in those applications. And we have projects where T-lens is doing that currently. And I'll also speak to you about something called wobulation or super resolution, where a product, not a T-lens, but our TWedge product is used to enhance the resolution of the display in the AR devices. So let's take cameras first. This is one of our reference designs. If you go to the poLight website, you can see a variety of different reference designs that we do. We do these for different applications, and we make these available to our customers. You can download ZMax, you can download the simulations and mechanical designs. The one I'm showing here is an add-in design. So by add-in, I mean the T-lens is incorporated into the lens barrel, into the optical stack. And this is a camera designed for AR applications, and it's very similar to ones that are used in some of our customer projects just now. When we design these reference designs, typically we'll work with a customer and take from them an initial set of very high level requirements, things such as what field of view do they require, what F number, and what's their target image sensor, either pixel pitch or optical format for the image sensor. And with just that information, we can turn out a fully spec reference design such as this. We'll provide a simulation of a whole lens system incorporating the T-lens. We can work to iterate that with the customer, and once the customer's happy with the specification of it, we can add in manufacturing tolerances for the lens and the camera module company, and turn out a fully parameterized, sensitivity analyzed reference design ready to go to manufacture at the camera module company. As an example of one of these, you see a camera module here. This is from one of our Asian camera module partners. This is based on the design that you saw previously, and has the T-lens incorporated as an add-in into the optical stack. So I mentioned we also do beam steering devices or super resolution devices. We call this TWedge. So TWedge, instead of focusing light, is a beam steering device. It is based on exactly the same technology platform as T-lens, the optical membranes, the polymer, and the piezo actuation. But instead of inducing a sphere on the membrane, here we tilt the membrane to form a wedge of variable angle. And by doing that, that allows us to deflect a beam in angle space as it passes through it. This is used for display wobulation. You might be familiar with display wobulation from DLP projectors. If you have a 4K DLP projector, cinema projector at home, it's probably got a wobulator in it. You'll be able to tell if it does or not, because that wobulator probably makes an annoying whining sound. And that whining sound, the audibility of that technology, is the main reason that previous technologies for wobulation can't be scaled and used in AR devices. So we looked at that problem, and we thought that using the poLight technology platform, we could make a wobulation device that was extremely low power and inaudible to enable this to be used in AR devices. And this is exactly what you see here. So the purpose of the device, as the image is projected through it, the device will shift that projected image by half a pixel left, right, up and down. And by synchronizing that with changes in display, it allows you to increase the resolution of the display fourfold. And you see in the poLight logo to the bottom right there the effect that has on image perceived by the user. This product is currently at TS stage, so we're sampling this to customers. Currently it's 10 by 10 millimeters. The next variant of that due out very soon. It'll be shrunk to about 8.5 by 7.5, and the mass production part will be smaller again, although actual numbers have yet to be fixed together with customers. We've made very many demos with the TWedge. So we've made, aside from our first initial proof of concept, we've made demos with TI DLP devices, with micro LEDs from companies like JBD. And the demos that we currently have in our labs are based on waveguides and will be direct viewable or potentially wearable. This final slide I'm going to show you today, I'm aware that I'm running over, is the perceived effect of the resolution enhancement that you get by using the TWedge. This is a direct viewable application, and this is using a micro LED display. On the left, you see the system with native resolution, as it would be without the TWedge. And on the right, you see the resolution enhancement that's achieved with exactly the same projection, but using the TWedge to increase the resolution by shifting that image left, right, up and down. And that's the final slide that I'm going to show you today. So just in summary, poLight T-lens, combination of tunable actuators of polymer and membranes, low power athermal optics. So, thank you.
Thank you very much for the nice presentation, actually. Really appreciate it. So you may have answered this question, but I think the first question is the question is liquid lenses versus T lenses. I'm not sure if the audience wants you to give more benchmarking or more insights, or but maybe if you could just discuss around this theme.
Yes, I mean, there are lots of different technologies and ways of making tunable lenses, and quite often all of the tunable lens technologies are sort of lumped together under the general banner of liquid lenses, whether they include liquids or not. So as I mentioned, we use a polymer which isn't actually in the liquid phase. There are a number of advantages of doing that. The main one being that our polymer is unaffected by gravity. Many of the pure liquid systems, there's a competition between the intended movement in the system, the deformation or the tuning that you want to happen, and the effect of gravity on the liquid, or liquids plural, depending how it's implemented. Essentially, there's two different ways of doing, or three if you include liquid crystal lenses, which uses liquid crystal display technology. But the main two technologies for liquid lenses are pressure controlled systems, where you have a liquid constrained within essentially a balloon, and you squeeze that, and as you squeeze it, the balloon bulges, and that forms the sphere. That's how companies like, for example, AdLens and Optitune make their liquid lenses. And there, the big challenge is controlling the quality of the sphere, because you're reliant on the physics of the membrane to stretch and deform equally. And also you're battling gravity, which is trying to pull your sphere in the opposite direction. However, the advantage of those systems, the advantage of the pressure-controlled systems, is that they're scalable in size. So if you want a very large lens, if you want something maybe 30 millimeter for the primary lenses in spectacles or Vergence accommodation, then probably a pressure-controlled liquid is the way to go. But if you don't need those very large sizes, but you do need small power consumption, small size, and very fast speed, then TLens is probably the better match. I think there's probably applications for all the different technologies.
Very nice. Thank you. I wonder if you can tell us more about the actual polymer. I know you said it's your secret sauce, but I know if you can just explain a bit more about kind of at least the material class that is there, or something.
Well, what I can tell you about it, yeah, I mean it's an extremely high transmittance, extremely stable, high Abbe number optical material. We ship it as a binary liquid, so it's shipped as a two-part liquid that's then mixed prior to assembly at our chip or packaging houses. That's probably about as much as I can share with you on it at this stage.
Okay, understood. There's another question, which is, can T lenses be used in metrological devices?
So T lenses can be used in all different sorts of applications, and the slide I showed earlier gave an example of just a small number of the applications that we're used in. So yeah, we're used in a number of different metrology applications. We're used in many scientific. We're used in research applications. So we've got the T lens is used, for example, in a brain imaging system from a Norwegian university called the Kavli Institute. So many different types of applications and use cases.
Okay, very well, very well. So, and I guess the last question is, how do you scale to volumes? I mean, so you mentioned that a few microliters could be used for how many devices? I forgot.
So what I said was that each device contains about 1 microliter. So
I see. I misunderstood.
Yeah, so with just 1 liter, you can make, in theory, if you don't lose any, a million lenses. But the polymer is extremely scalable because of the low volumes required, and everything else in the technology platform is developed to be high volume compatible. So the MEMS comes from a high volume MEMS wafer fab. The assembly techniques use relatively straightforward pick and place capabilities. So it's all designed to be capable of scaling to extremely high volumes. Essentially, we're targeting the smartphone and high volume consumer markets. So everything has got to be able to be extremely scalable to volume.
There's another question about, if I understand right, for the laser beam focusing, what is the range of focus?
So, well, as I said, there are two different devices, and the difference between them is aperture and optical power. So the range of focus is related to the optical power that we have. For most laser applications, we don't need the full aperture, so we would use our silver device, which has about 14 diopters of range available. And in the laser focusing application I mentioned previously for LBS displays, we're using that silver device. We're also working with other companies building out products and devices run about TLens specifically for laser applications.
Very well. So thank you so much